Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about parametric model estimation. So first, let's set up the agenda. I hope the screen is visible. So we'll discuss about parametric model estimation. Okay. So we'll discuss about what does this parametric model estimation means, and then we'll discuss the two broad philosophies. Okay, of parametric model estimation. One is the frequentist philosophy, and other is the Bayesian philosophy. So under frequentist philosophy, we'll study maximum likelihood estimate that gives a point estimate. So this gives a point estimate, and then we'll discuss about Bayesian statistics. Okay, under which we'll talk about two more point estimates, that is MAP and MMSE, but that I'll cover in another video. So these are not covered in this video. I'll create another video after this. Here we'll cover only we'll set up the philosophy. What is parametric model estimation? What is maximum likelihood estimate, and what is Bayesian statistics? We'll have a good understanding of these three topics. So let's start one by one. So first of all, what is parametric model estimation? What does this mean? Parametric model estimation. So there are three words: parametric model. Model leads to ML model in our context, machine learning model. And estimation means we are doing some estimate. Parameters means there are some parameters. So when we talk about parameters, what do we mean? Parameters for what? So generally, whenever we talk of parameters, as we have been discussing till now, we think of parameters for our PDFs, probability distribution functions, PDF, PMF. So there we have parameters. Okay, and then the model. And then we have estimates of the parameters. So parametric estimation means what will be the parameters of a model, and we'll estimate those parameters. And the model is the ML model which is describing our data. So parametric model estimation means we assume that our data, so we have some data. Data is like, for example, this is x1, x2, xn. Okay, is generated IID. IID means independent and identically distributed. Independent means all these data, all these samples are independent. And ID means identically distributed, means all of these are coming from the same distribution. Okay, and that's what parametric model estimation talks about, that we assume that the data is generated IID, independent and identically distributed, and this is this is generated from some known distribution. Okay, some distribution. Then distribution was that ID would be some distribution, say P of x given theta. So this is my distribution, underlying distribution from which this data is coming. From our experience, we know generally whether whatever this data we are talking about, whether it's for example, whether we are dealing with a Bernoulli data, which is like a success failure, or we are talking about height of people in a city, which will mostly be a Gaussian or normal distributed. So by experience of the data that we are handling, we will know what is the underlying distribution. Okay, and then we try to estimate what will be the parameters of that model. Okay, which will provide, okay, which will tell me, under which the probability of seeing such data is maximized, the data that we are having. Okay, say for example, if I have a if we say that this we are seeing a height of people, we have that data, for example. So we assume that means from experience we know that this will be a Gaussian distribution, normal, right? And we'll have to estimate the parameters of this. So the parameters for a Gaussian will be mu and sigma. So this is the mean and this is the variance. So we need to estimate that parameter. So we assume that the data, all these data points are coming from some known distribution, and we want to estimate the parameters given by this theta, which is mu and sigma in this case. Okay, and we want to estimate that under which parameters the likelihood of seeing this samples, that data that we have, is maximized. This is what it means, that this is the distribution. Okay, probability of seeing x given theta. Theta is the parameters of model, and this x is this x, the data that we have. Probability of seeing such a data, given that we know that this is the underlying distribution. So, and what should be the parameters of that distribution? Parameters of the better, instead of model we write distribution. Underlying parameters of underlying distribution, and we want to estimate this theta, which will maximize the probability of seeing the data that is in our case. It won't be a perfect fit always, that's why the data that we have will always have some noise in it, but we'll try to find the parameters which will be a best fit. Okay, so that's why we have a estimation rule. I hope this is clear. Parametric model estimation. So let me write it down for you so that it's clear. So in machine learning, we assume that whatever I've said, I'll write in line. We assume that the data whatever I have told you, the data d x1, x2, xn is generated IID from some distribution x, okay, some distribution whose parameters are theta, okay, and this is the probability of observing this data under this distribution. Okay, theta are the parameters of the model. So I have told you this. This is what parametric model estimation means. And this p of x theta, let me write it down that in English for you. This is p of x given theta. This is a conditional probability, if you remember. This is a conditional probability. Probability of seeing. Okay, let me write it down. Probability of seeing, this x is the data, right? Seeing data x1, x2, xn given parameters theta of the underlying probability distribution of the, I'll write only probability distribution. This is what we read it in English. Probability of seeing x, that is our data, given the parameters theta of the probability distribution. This is what it means. And we want to estimate this theta. This is what is parametric model estimation. This is the model. That if it is a Gaussian, I'll try to predict a Gaussian. My model would be a Gaussian model, and I'll try to predict the models mu and sigma, for which it will be the best fit, okay, to the data that I have. I have to predict that. That's what parametric model estimation means. I hope this is clear. And this is the distributions definition. That probability of seeing data given parameters of my probability theta of the probability distribution. Okay, for example, so this is the Gaussian. So for example, if you have Bernoulli, so I'll take the simplest example, that is Bernoulli trials, and I'll proceed with that. So for example, I have a coin with bias theta, okay, and we can model it as Bernoulli trial. What happened? We can model it as Bernoulli random variable, Bernoulli trials. Okay, so what will be the probability of seeing the data x given theta? This will be equal to theta to the power x into 1 minus theta to the power of 1 minus x, and where x belongs to 0 or 1. So, and this theta is the parameters of this Bernoulli, right? So this will be a probability of seeing heads or tails. So this will vary between 0 to 1. So theta will belong to 0 to 1. Okay. And we have seen Bernoulli distribution. If, for example, if x is equal to 0, what will this become? So probability of x given theta will become, so this term will become theta, and this is x equal to 0. So this will become 0. So this will become 1. Theta to the power 0 is 1. And 1 minus 0 will be 1, so this will become 1 minus theta. And if x is equal to 1, then probability of x given theta is equal to theta. Here only this term remains, theta to the power 1, and then 1 minus 1 will become 0, and this whole term will become something to the power 0 is 1. So this whole second term goes off because x is 1. So this is how this is just a revision of your Bernoulli. Okay. So this is our distribution, underlying distribution. And for estimation, so for example, we have a series of coin toss and we want to estimate the biased theta of the coin, if it is not 0.5, if it is a fair coin. For that, this is the formula. And we want to estimate this theta. Okay, so what is the goal? So that it can, so we have a set of data, some set of data we have, x1, x2, x2, xn, random, some data points. Okay, IID of Bernoulli trials, and now I have to estimate the parameter theta, which will best describe my data, okay, to maximize the likelihood. So let me write what is the goal of estimation. So my goal, what is my goal here? What is the goal to estimate? Because this is estimation, everything is estimation. We won't get an exact fit because remember the data will always have some noise. So we'll estimate the best fit there. Okay, so we observed data D, we observed data D, x1, x2, xn. Okay, to infer the parameters theta of underlying. So this is my goal. We made some observations and now we want to infer the parameters of underlying probability distribution. So, as I mentioned earlier, most of the times we will know by experience. So if you see here, right, as soon as we talk about coin toss, we'll know this is a Bernoulli trial, success failure case, 1-0. Okay, and if you have like height of people, then that will be a Gaussian. So these are some very common use cases. Okay, so we'll know what kind of underlying distribution it will be, and now only we need to estimate the parameters theta of that model. In Bernoulli, we just need to estimate the bias theta, and we have the formula. And in Gaussian, we have this two parameters, mu and sigma. Okay, the steps will remain the same. The theory will remain the same. The only difference will be the way, okay, the calculation will be different because the PDF will be different for both of them. Here the PMF is this, and then for Gaussian we know the PDF. So this is what we want to do, that we want to estimate the parameters theta given the data, which will best justify my data. So there are two philosophies, two schools. Okay, so there are two philosophies. As I mentioned earlier. The first one is frequentist. Okay, so the frequentists say theta is fixed. Okay, this says that theta is fixed but unknown. So it is fixed one point. It is fixed at this 1 point estimate. This is one way to give a point estimate. That is 1 point. Theta, if this is one value will be given. If theta, say for example, here if I'm getting, so if it is unbiased, it will be 0.5. I can get a 0.6 or 0.9 for heads, okay, for success when we say theta, okay, or it can be less also. So we will get one value. So that's what it means, that theta is fixed but unknown, sorry. And that's what we need to find out, but unknown. And the word frequentists comes from that it views probability as a long run average of repeated trials. Frequentist, how do they see probability? Say they see probability as, they view probability as a long run, as the long run frequency of events. Long run frequency of events, that is repeated trials, means tossing a coin multiple times and then see how many times heads is coming, and then we from that we figure out, okay, this is it a fair coin, what is the probability of seeing a heads, that's what the parameter theta of that. number of feds or number of successes is equal to the parameter theta. It can be 0.5, 0.6, anything between 0 to 1. Okay, that is repeated trials. For example, toss a coin multiple times. Okay, and then we count number of heads or tails. I hope this is clear. This is the frequentist approach. We do frequent, okay, long run based on the frequency. The second is the, and this is why this is favored. So this frequentist approach is favored for large. Okay, this is favored for large data set. Large, when we have large data set, means n is large. N is large. Then we go for frequentist, because we have seen in the central limit theorem and earlier law of large numbers also, right? When we have like very large number of data points, from that we can get a very good estimate. The sample mean would be equal to the population mean. Okay, so this is favored then. And the second approach is the Bayesian approach. So these are the two broad ways of estimating the model parameters of a model. The second one is Bayesian. Bayesian means, what Bayesian says that the core thing, the difference here, it said that theta is fixed. Bayesian says that theta itself is uncertain. Theta is uncertain. It is not fixed. Okay, so model it as random variable. It is not one point, but a distribution. Okay, so model it as a random variable with some probability distribution. Okay, so the main difference, the frequentist said that I will get a theta which is fixed, 1 point estimate. Here it says that theta is uncertain and I'll model it as a random variable which will have some distribution which I don't know. Say for example, if this is Gaussian, okay, Gaussian. So I will estimate the mu and sigma of this distribution, whatever, I don't know what is the underlying estimate, but it is not one point. It is a whole spectrum of values that theta can take. That's the main difference between frequentist approach and Bayesian approach to find what will be my parameter. Here I got only one value. Okay, I wanted to estimate the parameters of the underlying distribution based on the data. In frequentist approach, I had only one value. I will get only 1 point estimate, and here I'll get a range of, I'll get a complete distribution. Okay, I hope that is clear. And what is more around Bayesian, whenever you listen the word Bayes, right? So it comes from Bayes theorem. So underlying, this is coming from the Bayes theorem. Okay, it views probability as a degree of belief. What Bayes theorem says, views probability, how the way they view probability is different. Okay, so one was this, and this was, it views probability as the long run frequency of events, and from that it calculated how many heads, how many tails, what's it. It views probability as degree of belief, as degree of belief. Okay, that can be updated in light of new evidence. I hope you remember this. I'll revisit this when I go back. Okay, when I'll discuss this in this. Okay, so we had a prior, I hope you remember, we had a posterior, and then we had the probability of evidence. Okay, the denominator probability of seeing the evidence, and then probability, and then this was the likelihood. Okay, prior, likelihood, evidence, and then this was the posterior. So in the, when a new evidence, it is coming from, where does Bayes theorem comes from? It comes from conditional probability, right? So in the light of new evidence, the degree of belief that I had about an event, that needs to be updated. Okay, and that's how Bayesians view probability. Okay, and the frequentist view probability as long running average. of repeated trials. That's the major difference. And the other is, that in frequentist, theta is fixed, that is one parameter, and here the theta is a random variable with its own distribution. So these are the two major differences. And then now let's see how frequentists they do the estimation, and they will get point estimates, and how the Bayesian they do the estimation of the parameters, that is parametric model estimation, and we'll get a complete distribution. Okay, so first thing first. And what is one more thing, one more point is that this is favored for small data set, because in the absence of enough information, we can make the estimates based on the prior information I have. Okay, so because it uses the Bayes theorem inherently has prior, okay, because it uses prior information to make the estimation, prior information about the theta, what will be the model, what will be the parameters of that model. It uses the prior information that we have already, and based on that it will make the estimate. So whenever we have a small sample size, the samples are very small data set, we prefer Bayesian. There we can make the use of the prior information that I have about the data, and using that prior I can make the estimation. But when we have lot of data points, okay, then I can go with the frequentist approach. Okay, I hope this is the broadly these two are the philosophies, and both the philosophies are clear. Now let's get into the frequentist approach. Okay, so under frequentist approach we do a long running average, and there are two, the one which we are going to discuss today is maximum likelihood estimator, MLE. It gives a 1 point estimate. Okay, there are others also, which is called method of moments, which uses the moments of the underlying distribution, such as mean, variance, that is first moment, second moment is variance, third moment is skewness, fourth moment is kurtosis. These are the 4 important moments, and based on that they make an estimate. I'll not discuss about that. That is not so popular. The popular one is maximum likelihood estimator, which is called MLE. So I'll discuss about under frequentist. So first one is under frequentist. So this is coming under frequentist, undirected. So this is your maximum likelihood estimator, or MLE. Okay, the other one which I said is method of moments. This I'll not discuss, but this is on the similar lines as I mentioned earlier. Okay, now let's focus on maximum likelihood estimator. So this is a frequentist, and this is the most popular. Why am I discussing this? Is because this is just a note. MLE is the most popular frequentist approach. This is for model parameter estimates. Okay, this is the most popular. Okay, and this as I mentioned, this finds the parameter of the model, or the underlying distribution of the model, of the underlying probability distribution that makes data most probable. If I have this parameters, then this is the highest likelihood of seeing such a data that we have got, that we have observed. So using this parameters describe the data that I've observed in the best possible way. So that's what it says. So what is the likelihood function? So this is maximum. So let's define some terms. So it is maximum likelihood estimator. So estimator, we know it does some estimation. Maximum is like it will maximize the likely. Okay, what is likelihood here? So let's define likelihood here. So what is likelihood? I have already told you, but let me do it formally. Likelihood. So what is likelihood? Likelihood is, say for example, I have x1, x2, x2, xn are discrete For example, okay, discrete random variable. So this is the observations, this is the data observed with some discrete. So we have PMF and we have P of theta sum. So this is my PMF, probability of with some theta. So I am, these are my observations. So this is my observations or this is the data, same thing. Okay, so what is my likelihood function? So likelihood, so what will be my likelihood function? So likelihood function will be is the probability of observing x1 x2 till xn or this random variable given the parameter theta, whatever I have told, p of x given theta. In words, let me write it, is the probability of observing x1 x2 xn, okay, given the parameter theta, whatever is the parameter of my underlying model. And what is the probability? So this is my likelihood, and I have to maximize the likelihood of seeing such a data. That's what this estimator does. So I have to maximize this likelihood, and this estimator estimates the parameter which will maximize the likelihood of seeing the data that we have observed. Okay, so it's written using L. So this is the L is used multiple places. Okay, so here also I'll use the same. So L, as we go on, so this L is used again and again. So here it is used for likelihood. Okay, I'm using, so L x1 x2 xn of likelihood of seeing the data given the parameter theta is probability parameter theta x1 x2 dot dot xn of probability of seeing all this data given the parameter theta. This is what is my likelihood. Now this can be written as product of all this. So this is my joint probability, and since my assumption is that the given discrete, I missed the term, the important term here, IID, that is independent and identically distributed. So identically distributed is coming from this PMF. Independent means all these observations are independent. So the joint probability will be the product of all the probabilities. So this will be probability of theta given x1 into probability of theta given x2. That was theta x1 x2 like that, into. That will be product of that. We know that from the past. So product of all of this. So pi is equal to, this pi symbol means product, sigma. This sigma means sum, and this pi means product. This is a symbol that is used. This is add, and this is product, multiply. Okay, pi, this is equal to probability of given theta, parameters theta, observing this data xi. Okay, since IID. Okay, and if it is a continuous, then what will be? So this will be continuous, then it will be integrate over theta, f of theta xi d theta. This is for continuous case. This is for discrete. P theta, f theta. Okay. This is for continuous random variable case. Now let's continue. So I'll continue. This is just for your information. Okay. So we'll continue with this only. And now we have to estimate that what will be this product. Okay. So we have to find the value theta which maximizes the likelihood of seeing all these values. Okay. So what is my task? To find theta for which likelihood L is maximized. Likelihood means likelihood of observing this data given the parameter theta. So this is my task. So whenever we talk of maximizing something, how do we do? So that becomes an optimization problem. Optimization also have another video on calculus. I'll put that in the link if you don't understand. So generally, whenever we want to find the maximize or minimize something, that is coming from the calculus, right? We want to find what is the maxima or minima of that function, right? So what do? We differentiate it and equate it to 0 to find the point where this will be maxima or minima. In our case, we want to maximize, so we will find the point where it will be maximum. So that differentiation, the first derivative will give me the value where this will be a maxima, argmax. So how do we write it? Let me write it technically. Argmax theta. So the maximum argument theta L x1 x2 xn theta is equal to theta ml. So x1 x2 xn, and this is equal to, so this is my theta ml is maximum likelihood estimate. So I'm doing this is just the symbols that you should know. This is pi I equal to 1 to 1, probability of theta, probability with parameter theta of observing all the xi's given parameter theta. Okay, so this is theta ml means maximum likelihood. This is the parameter max likelihood we want to find out. This is same as this. This is how we write it. For maximizing, again, as I meant, how do we find? We differentiate and we try to find out. But here, if you see, we have a problem. We have a product. So taking the differentiation of a product of multiple numbers is difficult, right? So from the derivative formula also, right? For taking that is a difficult thing. What is easier? If it is in the form of sum, okay? So if you have like multiple variables, x1 into x2 into x3 into x4 like that and xn, and I want to do d by dx of this will be difficult. If I have x1 plus x2 plus x3 plus x4 like that till xn, and if I want to do d by dx of this, then this will be easier, right? So let's make it easy. So how do we make it easy? A general way in all across machine learning, you will find that whenever there is a product, what do you do? What makes a product a sum? So there's a function called log. So we take log on both sides. This will make my product into, convert the product into sum. We know that. And also log is a monotonic increasing function. So as x increases, log will also increase. So this doesn't impact. So we can easily, happily take log. So we had, this was L was my likelihood. This was my likelihood. So after taking log, okay, it becomes log likelihood. So we say that it becomes, after taking log, we take this becomes log likelihood. And we tell it as L bar. Okay, and this is equal to log of pi I equal to 1 to n p of theta x of I, and this log will convert this product into sum. Sigma I equal to 1 to n probability of theta x of I, and this is L bar. L bar is log likelihood. So again, we have to find the theta that maximizes this sum now. Okay, so my theta ml would be, so my theta ml maximum likelihood for observing this data parameters, which will maximize the probability of seeing such data, will be equal to argmax of theta, and this is L bar is log likelihood x1 x2 xn of theta, and this log likelihood is this summation of all the probabilities. So this is how we find it. So let's understand this using a simple Bernoulli example. So for example, what am I saying? For example, now, so we have again x1 x2 like that to xn, IID, Bernoulli random variable, probability of xi equal to 1, so it is success or failure, success is 1 is equal to theta, and probability of xi equal to 0, that is failure, is 1 minus theta. This is how Bernoulli is defined. Okay, and we have to estimate this theta. Task is estimate theta ml, maximum likelihood, okay, which will maximize the likelihood of seeing such data. This is my task. So here let n1 is equal to number of ones in x1, x2, xn. So there are n trials, right? So here it can be 1, here can be 0, here can be 0, here can be 1, like that. So what is the total number of ones in this n trial? So that number of ones is n1. So and total number of this is n. So what will be my n? So this will give my n0 is equal to n minus n1, right? So remaining will be number of zeros, but I'll just use this n1 and I'll formulate this. Let's see. So my likelihood would be, just I'll put all the formula here. Likelihood L of x1, x2, xn for this parameter theta would be equal to pi I equal to 1 to n. Probability of theta xi, I'll be fast now, so that you know this is just a repetition of what we have done. So this is equal to, from Bernoulli, you know, theta n1 into 1 minus theta n minus n1, success, failure, count, total. This is probability of success and probability of failure. So this is how it is. So this is my log likelihood. What will be my log likelihood? L bar is equal to log of theta n1 into 1 minus theta n minus n1 is equal to log of this thing. This is multiplication. So this will be log of theta to the power n1 plus log of 1 minus theta to the power n minus n1. You know, with log, this n1 comes here, this power will come here in front. This will become n1 log theta plus n minus n1 log of 1 minus theta. This is my log likelihood. And to maximize, okay, so my theta ml will be argmax. This is how we write argmax theta, that maximum argument theta, which will maximize this thing, this upper term, my log likelihood, that is n1 log theta plus n minus n1 log of 1 minus theta. So how do we take this? Okay, so for finding this, as I mentioned, so for maximizing anything, this is an optimization problem. We take the derivative with respect to theta and equate it to 0. Take derivative to find maximum, right? To find point of maxima, take derivative and equate to 0. This implies d by d theta of n1 log theta plus n minus n1 log of 1 minus theta is equal to 0. This implies what will be this. So differential of log theta is 1 by theta plus n minus n1 is constant with respect to theta, and log of 1 minus theta will become again 1 by 1 minus theta, and again there is a negative sign, so this is chain rule. So this will give a minus 1 because theta has minus theta, so this will become this is equal to 0. This implies n1 by theta is equal to this negative, I can take it on the other side. So this will be equal to n minus n1 by 1 minus theta. This is simple math now, simplify it. This implies n1 cross multiply n1 minus n1 theta. This is equal to n theta minus n1 theta. Okay, so n1 theta is same on both sides, cancel it out. So this implies n1 is equal to n theta. Sorry, what have I done? N1 minus n1 theta, this will be here, okay, and n theta minus n1 theta, this is gone, is there? So we'll take n theta is equal to n1, this implies theta is equal to n1 by n, and this theta is my, what was I doing? This is my theta ml. This is what I was estimating, right? So maximum likelihood will be at n1 by n. What is my n1? So this is the ratio of, this is what did it give me? This is number of heads, this is total number of trials. Total number of trials. For example, so this will give me the parameter theta of the success. For example, if it is like, so I have say for example 10 observations, 10 realizations or observations. One, zero, 1, 0, 1, 1, 0, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. Okay. So my theta will be equal to number of, this is by 10. How many ones are there? 1, 2, 3, 4, 5, 6, 7. Right? This implies theta is equal to 0.7. This is my theta maximum likelihood. So theta ml is 0.7. I hope this is clear. So this is equal to the probability of 1 from observation. This is equal to probability of success, or probability of x is equal to 1. This is what it is giving, right? Probability of x equal to 1. And this is what it is giving. This is the maximum likelihood. So my theta would be, if I have these observations, so my theta will give me the number of, and that's what it is. This is what it should be. And if it is like n is very large, it will give me better outcomes. What it is in this random sample, I had 7 heads out of 10, or 7 successes out of 10. Okay, I hope maximum likelihood estimate is clear. Similarly, you can do the maximum likelihood parameter estimation for Gaussian distribution also. Okay, I'll leave it for you as an exercise. Let's go to the Bayesian now. So as I mentioned here, what was the main learning? That will give me a fixed estimate, one value, and this is coming from a number of repeated trials. So this is number of repeated trials, and when n is big, this makes sense, and it will give me a one value, 1 point estimate. Okay, this is coming from the Frequentist. This is maximum likelihood estimate. Next, so we talk about Bayesian statistics, the second philosophy. So within this, so what did we say? That this is a Bayesian approach, right? So Bayesian approach, we mentioned earlier. Bayesian approach views a model's parameter as a random variable, which needs to be estimated, right? Models parameter theta, which needs to be estimated as a random variable, means it is not 1 point but a complete probability distribution. Okay, that has probability distribution. And because of this Bayesian approach, so this is one random variable, and then this lets us include the prior information about the distribution of the whatever theta it had. So there will be some prior information about the distribution of theta. We can include that. Very helpful when the sample size is small. Useful for small data set, where I can use the prior information to estimate what will be my parameters like. Okay. So, and the Bayesian inference is the computational process of finding posterior distribution of the theta based on the prior and the data that I have. The prior information plus the data, okay, that will give me the posterior distribution. That is the final probability distribution of the parameters theta. In Bayes theorem, how did we write it? So, for example, let's revise Bayes theorem. So, Bayes theorem, I'll write it in terms of our context, parameters, the theta and the data we have. So again, x1, x2, x is my data and theta is the parameters that I want to estimate. Okay, so how do we write it? Bayes theorem, probability of theta. This is capital theta. Okay, this is my capital theta. Okay, theta, probability of my theta given my data x is equal to probability of theta alone into probability of x given theta by probability of x. Okay, so this is my posterior distribution of theta after I have seen the data x. Given this data, what is my parameter theta? This I want to estimate. This will be my estimate. So given this data, what will be my parameters distribution? This theta is the distribution's theta. This parameters of the distribution, and this theta is the this theta itself is a probability distribution. Okay, so what is the probability of my parameter probability distribution of my theta given the data that I have? And this is what is probability of theta? This is the prior, that before seeing the data, this was the prior information. Before I had the data, I had some initial belief about the parameters of the model. I will have that. Oh, there's one thing, right? I will have some idea about the model that I'm going to use. What is the underlying distribution of the model? And I will have some prior belief about the parameters of that parameters. Okay, prior belief of the parameters. For example, if I have a coin, I am tossing it. Okay, if it's a fair coin, then I will have a prior belief, right? It's a fair coin. If it's an unfair coin, I will have a prior belief that it is unfair, and I will also have the notion that whether it's biased towards heads or biased towards tail. Okay, and I can use that prior information, prior belief, to model my parameter. If it is unbiased, then no problem. Okay, then it will give me whatever it is. Okay, but if it is biased, if I know that my coin is biased towards heads, so I will use that information, and whatever the posterior, after that, whatever parameters I get about that distribution, that will show that this is biased towards heads. Okay, my theta is biased towards it. I will use that information, and finally I won't get a depending upon my prior belief. But earlier, when it was like fair coin, I will have a different distribution, and if it is the biased coin, biased towards heads or biased towards tail, I will have a different distribution based on my prior. This is the broad understanding, and let me now continue on the problem, the terms and their definitions. Okay, this is a likelihood as we saw earlier. Likelihood of observing the data given my model's parameter theta. And this is the evidence. What is the evidence? Evidence is the data that I have seen. Data or the observations. This is the evidence. So based on this evidence of the new data, what is the parameter? I had some initial belief. Okay. And then based on the parameters of this belief of this parameters theta, what is the data? Okay. And then this is the evidence, the observation of the data that I have. And this is my posterior, that after observing the data, what is my parameters theta. I hope my Bayes theorem is clear again. Okay. That's why I stress so much on Bayes theorem. I'll put the link of that video also in this description. Okay. So let me write it down, whatever I have said in words. Probability of, okay, theta. Yeah, this is my prior. So this is initial distribution. Initial distribution of theta. That is before seeing that data. Before seeing data. Initial distribution or initial belief. Okay, this is my prior. The next is probability of x given theta. In my likelihood, as the likelihood we have seen earlier, likelihood is conditional distribution of x. Okay, probability of seeing data. Probability of seeing data x given theta. And then probability of, this is my posterior. Okay, this is probability of parameter theta given data x. Okay, so these are the things that you need. I hope this is clear. Whatever I've said, I put it in words so that it's clear now. This is the formula. See this in one page. Okay. Let's proceed. So let's see. Okay, same example. For example 1. So we have one x1, x2, xn, okay, are IID Bernoulli with parameters theta, and x1, x2, xn are the realizations or observations, okay, of theta. Okay, my theta belongs to this probability 0 to 1. Success, failure, coin tosses, whatever you can take these examples, are realizations or observations. Okay, and then as in the last one, n1 is equal to number of ones in n trials. Okay, so let's go one by one. What is my prior? So my prior belief is, this time my prior is that theta is uniform. Okay, uniform. So let it, okay, uniform 0 to 1. Let this be continuous so that I can give you a continuous example also. It doesn't make any difference here, but this will just give you that this can be continuous also. Okay, so my f of theta is equal to 1 in the is equal to 1 in 0 is less than x is equal to 1 and 0 otherwise. This is how my PDF is. So initial PDF of the theta is given that it is uniform between 0 and 1. Okay, so how will this look like? Uniform distribution. This is 0, this is 1. So this is, say for example, this is 1. Okay. Say this is the PDF, this is the area under the curve. Okay, this is my PDF. PDF of uniform distribution of random variable theta. Okay, this is what PDF. So this is all the values. So for example, if this is 0.1, 0.2, like that, 0.8, 0.9. So whether my value is between 0.8 and 0.9, here I can give a range only, right? Or where it is between 0.1 and 0.2. So both these values are same. Whether so the probability of finding a value of the theta, that is probability of theta of success, or head, say if it is a coin, right? So probability of head, it's a okay, the bias of the coin, probability of head, whether it's between 0.1 and 0.2, or whether it's between 0.8 and 0.9, the area under the curve is same. So that's what uniform means. So it's not biased towards any value. So this is a uniform distribution. Okay, so it's equally likely to have my theta in this. All these ranges are equally likely. This is what. So this is the prior belief I have. Okay, what is my likelihood? My likelihood is P of x, x given theta is equal to, for Bernoulli we know theta to the power n1, 1 minus theta n minus n1. This is the likelihood of seeing the data x given my parameters of the model theta. We have seen this already. And then my posterior, after seeing the data, probability of theta given x is equal to, will be given by, this is equal to, so I'll write the Bayes theorem formula. I'll take it from here, this thing, let me copy it. And here, this is, since this is continuous, I'll write fx of x, my marginal. This is my marginal probability, and here instead of p, I'll write again f, because this is continuous. I've assumed this to be continuous, so that's why this f is coming, just to be correct with respect to the symbols that I use. Okay, so this is marginal. So we know this prior distribution, this also we know. So this prior distribution, we know this f of theta, so this will be my f of theta here also. F of theta. So I know this f of theta, this is a uniform. Okay, I know this is my Bernoulli. I don't know this, and okay, let me see what it is. Okay, I don't know this. For calculating this, I want to calculate this. I have this information, I have the prior, I have the likelihood, I don't have this information. Now this is the tricky part, and let's see what all things we do to find this out, this marginal probability. Some things we'll use from the past, okay, the conditional and all. So we know from the past, right, what is the marginal probability, what is the formula. So for example, fx of x, so this is the marginal, this is equal to, I can integrate the joint with respect to the other variable, I'll get the marginal probability. I'll put that link also if you don't understand what am I saying. Okay, dy, so this is the joint, this is my marginal, and I'm integrating it with respect to other variable to get the marginal. If I integrate the joint with respect to other variable, I'll get the marginal for. Nice. So I have the joint probability here. Do I have that? Let's see. So also from conditional probability we know that. Okay. So this is what we know. So this is my question number 1. And then from conditional probability, we know what is the conditional probability. F of x given y, this is equal to, conditional is equal to joint by marginal. Here y and y will same, x given y, so y will come here. So this is your conditional probability, this is your joint, this is your marginal. Okay, so I want to find, this is what I want to find here, this is what I want to find. Since I want to find this integration, if I have this in terms of fyy, this will be integratable. Let's see. So let's, this one goes multiplies here, so I will get this value. So this will be equal to f of x y, the joint probability, is equal to conditional, or the marginal, into conditional, f of x given y, x given y. So watch this, x comma is and, that is joint, and x given, these lines are conditional. So watch these symbols carefully, both are not same. This is joint, this is and, this is conditional, given. Okay, so I have this equation number 2. So watch this carefully. So I want this because of this. This I told, this marginal I can find it using joint. Now I want to find the joint, and this joint will come from the conditional that I have. Okay, fyy into this. So let's put this one, let's plug this in here. From 1 and 2. From 1 and 2, okay, we have fx of x is equal to integral over y, fy of y into f of x given y, x given y dy. Now it is in fyy terms. Okay, so I have got fx of x. Now let's plug this back in. So I have these two information, I had these two information, I didn't have this. Now let's plug this back in here. So let's continue from this posterior. So let me copy this. I want to plug that value. So this is from the Bayes theorem. So this value we have found. Okay, this is what is the value. This is equal to integral fy. Okay, and here what is fy? Here fy is theta, right? F of theta given theta into probability of, okay, x given theta capitals, x given theta small, d theta. Directly I put here y is theta, right? I gave you a generic formula. Here my y is theta. I'm talking x and theta, x and theta. Here x and y was x and theta. This is just for the formula. Here my y is theta. So plug that theta here. Y is equal to theta in this. For us, y is equal to theta. Okay. So this is f theta theta into f of f. Again, this was for continuous. Our case, this is Bernoulli, that is discrete. So this is, and what will be this range valid? This is valid from 0 to, this is not our complete pi. Where is the range of my theta? The theta is from 0 to 1. Okay, so now it's given that f of theta is equal to 1 because it is uniform. This is my prior. That's what we started with. I hope you remember that. This is an example. Prior is uniform. F of theta is equal to theta in this range. 0 to 1. Otherwise it is a. So here f of theta is, PDF is 1 everywhere in this range. So let's replace, put all these values in this. So my f of theta given x, this is capital, this is small, is equal to f of theta, this is uniform distribution, this is 1, into probability of x given theta, this is theta to the power n1, 1 minus theta to the power n minus n1. This is my Bernoulli PMF. This is integral 0 to 1, 1 again for this f theta into theta to the power n1, 1 minus theta to the power n minus n1 d of theta. Now this integral we have to calculate. Okay, this integral generally these nowadays integrals, these are very difficult to compute, these integrations. Okay, these integrals, okay, whatever, difficult to compute. That's the integrals are very difficult to compute. Okay, so for this type of formula, there is a known function already. Okay, there is a known function which helps to solve complex integrals. So there is a known function called beta function. Okay, there is a known function called beta function, which is of this shape, which will help me solve this problem. With beta function, what is beta function? So it is written as, this is a equivalent of this integration, so we'll use it directly here. So beta of a comma b, this is given as 0 to 1 integral t to the power a minus 1, if a, there are two parameters, and then 1 minus t to the power b minus 1 dt. Okay, so beta of a and b, it is t to the power a minus 1, 1 minus t to the power b minus 1 dt. So if you see this is equivalent to both of them, they look similar. Instead of t, just put theta. What it will become? Here it is a minus 1. So a minus 1 is equal to n1. And here 1 minus t is 1 minus theta. So let's put, okay, t is equal to theta. Then n1 is equal to 1 minus a. This implies, okay, sorry, a minus 1. This implies a is equal to n1 plus 1, and similarly n minus n1 is equal to b minus 1. This implies b is equal to this minus 1 will come this side, n minus n1 plus 1. Now if I replace this, now everything, now this is coming exactly in this format, this has come. So of t I have theta, and now for n1, a and b and t, everything is fixed now. How can I write it now? So now this can be written as, in this format, this integral 0 to 1 theta to the power n1, 1 minus theta to the power n minus 1 d theta can be written as beta function of a and b. A is n1 plus 1, comma n minus n1 plus 1. This is my beta, and this is a known. These functions are known, have a known curve. Generally these are like this, the curves are like this, not exactly bell shape, but close to. Sometimes they become equal, like bell shaped also, but they're close to that, and sometimes they take U shape for different values of a and b they take. But this is widely studied, and they have very known, they have right skew, left skew. These are very widely studied, and these are standard. So the distribution of this beta function, or beta distribution, this is known. So we modeled this integration into this format. I hope this is clear, this beta function part. So this integration is difficult, so we used a known, okay, this is a known way to solve complex integral, beta function. Known way to solve complex integrals. This is known. If this is, so we formulate this in this format. Okay, so we replace this. So what will be my posterior now? Posterior, what was the posterior? F of theta given x, is equal to, the numerator remains as it is, by beta n1 plus 1 here, comma n minus n1 plus 1. Okay, so this is my posterior, final posterior. So we'll use this formula. So this is my formula. So let's save it. This is my, so how did we get this? When the prior was uniform. The prior was uniform here. We mentioned this. Is uniform continuous. So this prior was uniform. For this, the posterior came out to be theta n1, 1 minus theta n minus 1 by beta function of n1. And this beta function is a known way to solve complex integral. This is difficult to solve otherwise. I hope that is clear. Okay. So now this is when the prior is uniform. We know that prior is uniform. What if, okay, what if we know that the theta is more closer to 1 or more biased towards 1? Okay, question. What if we have initial belief / prior information that theta is closer to 1? How will we incorporate this information? So we know we have a prior belief already. Earlier we assumed that theta is uniform. I have no prior, everything is equally likely, nothing doing. Okay, simple. But now we have some extra information that can be used to leverage that my theta is closer to 1. The probability of success is closer to 1. This is the same Bernoulli trial. The probability of success is now closer to 1. Okay, and my f of theta is given as, so my it's given a f of theta is equal to, it is twice of theta for all 0 is less than x is less than equal to 1 and 0 otherwise. So this is my PDF of the prior. This is my prior. I have this prior belief that my theta is more biased, and how much it is biased, that it is 2 theta. So if we draw the PDF, how will it look like? Okay, this is a prior. Okay, and then let's draw a line like this. Okay, so within 0 to 1 range. Okay, so the area should be 1. So that area will be half into base into height, half into 1 into height. So half is 1 into, then height should be 2. So this will be 2. Because PDF should be 1, right? PDF is equal to 1 always. The area under this curve will always be 1. This area. But if you see, right, earlier what was the case? So this is 2, this is, say, for example, 1. Okay. So earlier, if you see, when this was uniform, all the values, say for example, this is the strip, right? What we did. This is 0 0.1, 0 0.2, this is 0 0.8, 0 0.9. Okay. And this value here. And here if you do dot 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 dot. So if it was uniform, if you see this strip was, the length of this strip was equal to this length, okay? If this was uniform, both were equally likely, so no problem. But now if you see clearly, I'll rub this off so that you don't have confusion. And I'll color the inside area. Okay. Now if you see clearly that probability of finding something close to 0 is this area is smaller than this area, is definitely smaller than this area. The probability is increasing. This line is y is equal to 2x. Okay, so probability of finding theta, this is this is f theta of theta, and this is theta. Okay, so probability of finding a value, as if we are moving towards 1 towards x, the probability is increasing, the area under the curve is increasing. So we have, this is the prior belief that we have, that this is, that theta is closer to 1, and this is the parameter to define that. Okay, now with this information, let's proceed. So for example, okay, so this is our prior information, prior we have mentioned there. So for example, if n is equal to 8, and x1, x2, xn, okay, so this is like 1 0 0 1 1 0, 1 2 3 4 5 6 1 2 3 4 1 2 3 4 5 6 7 8 8. Okay, so what is that theta ml? What will be my ml estimate be like? N1 by n, that will be equal to, how many ones are there? 3 by 8. According to ml, this will be my estimate, theta ml. We have seen this from maximum likelihood estimation. This will be my estimate, 3 ones out of 8, right? But this is not including any information about the prior. This is just based on my observations. Nothing has been included. This is okay. Nothing, no information has been included from the prior. But such a pattern of ones and zeros, say if we have infinitely millions of observations, so in that, if you toss the coin like thousands of times, so can't we can't, even if my probability of seeing, even if my this thing, even if my theta probability of success is 0.99, can we deny probability of seeing 8 such events? My estimate is saying 3 by 8, but even if my probability of theta is like 0.99, we can still see such an event. Say for example, if I have millions of events, will this impact just 3 out of 8? And if my probability is 0.99, even for example, if I see 1000 events, 1000 tosses, and 990, okay, and out of that 10 tosses can be tails, out of that 990 would be heads and 10 would be tails. But here last 8 or in somewhere in the middle, I saw that this is a kind of thing where 3 are heads and 5 are tails. So I saw out of 10 tails, 5 tails I saw in this 8 tosses only, but it was somewhere in the middle. So the probability of seeing such a series of events is possible even if I have theta of 0.99. So this estimate does not guarantee anything. Okay, so just understand that probability of seeing this event is possible. We cannot deny the possibility of such an event. So what the point I'm trying to make is that this estimate is not using any information from the prior, and now we have prior information that everything is not uniform, but there is a bias towards heads. And now let's see. So let's see the posterior formula. Let's copy that as it is. What was the posterior formula? Somewhere I highlighted that. Now beta function, where was that? This one. This one. Let me copy this. So here we estimated. Okay. Let's do the example 2. Here, paste. This is for example 2. Okay. Here my prior is f of theta is equal to 2 theta in 0 is less than x is less than equal to 1, 0 otherwise. Okay, this is my prior belief. And everything p of x, this is Bernoulli, we know that likelihood. Let me write it down again. Likelihood is P of x given theta, P of x given theta, x given theta, x given theta is equal to theta to the power n1, 1 minus theta n minus n1, where n1 is equal to number of ones in n trials. Okay, so what will be my posterior with this formula? This is my posterior, right? What is the part posterior? F of theta given x, theta given x, this is equal to f of theta theta, this is 2 theta this time, into probability of x given theta remains the same, theta to the power n1, 1 minus theta to the power n minus n1, and this will be integral. F of theta was 1 earlier, right? This will become 2 theta into this, again I'll put it here, theta to the power n1, 1 minus theta to the power n minus n1 d theta. So again this is this integral difficult to compute. So we'll use the beta function. Beta function. What is beta function? Let me write down again. Beta of a comma b is equal to integral 0 to 1 t to the power a minus 1 1 minus t to the power b minus 1 dt. These are beta function. Let's substitute this. Let's do some computation already. This 2 and 2 will cancel out because this is this thing, and here this is between 0 to 1 because this function is defined between 0 to 1 only. Okay, so now let's do quickly. So let's just substitute this. It's done. So my posterior f of theta given x, theta given x is equal to so this theta will multiply this theta n1, so this will become theta to the power n1 plus 1 into 1 minus theta n minus n1, and here's what this and this theta will multiply. This will be integral 0 to 1 theta to the power n1 plus 1, and this is 1 minus theta n minus n1 d theta. So this, what will be this beta now? This will be equal to theta to the power n, theta to the power n1 plus 1 into 1 minus theta to the power n minus n1 by, what will be this beta value? Earlier we saw this was beta was n1 plus 1, here n1 plus 1 and n minus n1 plus 1. Here I have multiplied one more theta. Earlier it was n1, so there will be this one will increase by one more, right? This will become n1 plus 2, and the second term remain as it is, n minus n1 plus 1, right? So this is my posterior now. So did you see earlier this beta function will be different from this beta function? This beta of n1 plus 1. Okay, and earlier this numerator is also different. Here the numerator is also different, and the beta function below is also different. It will have its own curve, something like this somewhere. Okay, so that we will see. Okay, just now we'll see. So if we, so when do we use Bayes theorem? Okay, if we do not have enough data, if we do not have enough data, okay, if we do not have enough data, then we should not ignore our initial belief. Okay, but if we have enough data, say for example, if we have enough data, then that will automatically, okay, rule out, and we will come to a good estimate of the data. So this is only good when we don't have enough data, and this Bayesian estimation or Bayesian inference, this gives us a good estimate. Okay, it will give me a probability distribution. This beta function is a probability, beta functional distribution is a distribution. It gives us a curve, a distribution of the values. From this we'll get the distribution, and from that we can see. Okay, let me show you with this with an example, and then we'll conclude finally. Okay, so let me just a minute. So this is one example where our this will make everything clear. Okay, let's follow this. So I hope you remember our MLE. MLE is equal to number of ones by 1. Okay, and n naught is equal to n minus n1. So let's see all the graphs, and this will make it amply clear finally, and this will be the conclusion for Bayesian statistics and everything whatever you have studied. So my maximum likelihood estimate gives that my best theta is n1 by n. That's what is from the past. That's from the Frequentist. And from the Bayesian, okay, we have all these curves, the beta curves that I said, right? So this is the curve we are getting. So the prior distribution, how this influences. So earlier when the distribution is uniform, when the distribution is uniform, this is the blue line. So all the blue lines in this curve are corresponding to the uniform distribution. So let's see. And this is for the red lines are for the distribution when theta is equal to, the initial belief is that it is biased towards 1, and their f of theta was is equal to 2 theta. This is what this line is, 2 theta 1. Okay, so area under it is more biased towards 1. Here everything was more likely. Here if you can clearly see the area under curve here is greater than this area. The probability of seeing values greater than half is more here because this area is larger in the PDF. Okay, so in the normal distribution you can see that here the number of zeros is 1 and number of ones is 3. So what will be my number of so total number will be n will be equal to 4, n0 plus n1, and what will be my MLE, maximum likelihood estimate, that is 3 by 4. So if you see here, this is 0.8, 3 by 4 will be here somewhere 0.75. So this is my MLE when number of heads is 3 and total number of trials is 4. So 3 by 4, 0.75. This is my maximum likelihood estimate, this orange line. And then there is a red line, okay, which is corresponding to the 2 theta. That my prior information that I have is that that my theta is more biased towards 1. Then this line it's coming. So if you see here that this is coming here just less than this thing, it will be around 0.7 or something, I don't know. And then this blue line is there. This is where prior is uniform. So this is giving me even less value here in this case. So I hope this example is clear. So this is there. Similarly in this example here, if you see number of zeros is 3 and number of ones is 1. So here MLA will give 1 by 4, right? N1 by n. So total is 4, but here number of ones is 1 only. So n1 by n will be 1 by 4. So my MLE now, here it was 3 by 4, it was here. Now MLE has changed. It has become 1 by 4. And this blue line is giving me this prior information, where prior is uniform. So this is my blue line, and this red line's estimate is giving me, you see there is so much gap. This is giving me here around 0, it is more than 0.4. So it was 0.25, and this is where it is saying that it is more biased towards 1. It is giving me more than 0.4. See what is the influence of initial bias. I hope you are getting it. And when this n is tending to 100, so we have a lot of samples. Now you see everything will converge. All of them are very, very close. There is not much difference. So that's what I mean. For small samples, taking the prior into account will influence my my posterior. Okay, and these you can see these are the distributions, posterior distributions. MLE is just one point estimate. These are posterior distributions based on my. These are the Bayesian. All these curves are the Bayesian posterior. All these I'm not getting one value, but a range of values. This is the PDF. Okay, and when n tends to a large number or very high, all of them converge to become very close. That's what I mean. When the sample is very high, all of them become very close. Okay, that doesn't make difference to take into account prior value because the data itself speaks for itself. I hope this is clear. Okay, we spent a lot of time. I'll just quickly do a recap and then we'll done. Okay, so we are doing parametric model estimation. So what does that mean? That we want to estimate the models of the parameter given the data. That's what it means. And there are two philosophies. One is the frequentist, where frequentist model says that theta is fixed but unknown, and probability is a long run frequency of repeated trials. Okay, and then it is favored when the data set is large. And then there's the Bayesian philosophy, where it says that theta is uncertain and it's like a random variable. It's not one fixed point, one point estimate. Okay, and then it views probability as a degree of belief that can be updated based on the new evidence, that is Bayes theorem. And this is favored for small data set where the prior belief can impact the information, means the posterior a lot. And that's what we did all derivations around this. We saw examples, and then finally we came to this plot which sums up everything. When the data sample is small, the prior belief is giving me more biased data, more information. Okay, towards means it is giving me more information, more which is close to the prior belief when the data is small. But when the data is large, everything, this MLE and all the estimates for with uniform prior or biased prior, everything coincides into the same point. So when the data is large, the data speaks for itself. All this prior belief, okay, it doesn't matter then much. Okay, this was a long video, but thanks for watching. Okay, and have a good day. That's all for now. Okay, and bye for now.